Hello, my name is Alex Reid. I'm a staff scientist at the LINAC Coherent Light Source at SLAC National Accelerator Laboratory. And I'm the instrument lead for the megaelectron volt ultrafast electron diffraction facility. And today it's my pleasure to introduce this facility to you and tell you a little bit of why, even at the world's brightest free electron laser, we actually care about electrons as well. So this is an aerial shot of the SLAC site, just slightly west of Stanford University in Menlo Park, California. And as you can see highlighted here is the linear accelerator. So the linear accelerator now comprises of both a copper accelerator and a superconducting accelerator, both feeding high energy electrons to undulators to produce very bright, very fast X-ray pulses. So this is pulses with 10 to the 13 X-rays and only femtosecond durations. And these are fed then to 8 experimental hutches in the foreground, here in the near hall and here in the far hall, where the actual interaction points and science can be conducted. Less well known to this main linear light source and the main hutches is there is in fact a 9th hutch, the MeV-UED facility. This is a separate accelerator housed in another building at SLAC. However, what I want to show you today is how this facility is very complementary to the other 8 hutches and the X-ray facilities here, and give you a little bit of an overview of what we do, what is involved with this instrument, and how you can access this for your own science. This cartoon is a schematic of the MeV-UED facility. And the key point here is this electron source, or RF photocathode. So an ultra short beam of UV light, about 50 femtoseconds in duration, is used to create photoelectrons from this copper cathode. They're then accelerated by this extremely high power radio frequency field over only a few centimeters to the MeV energies that we use. They're then focused via a magnetic lens down into our interaction point. Here we use both solid, gas, and liquid samples and probe the structural information by passing the electrons through. The electrons, which are scattered by the atoms within the sample, then encode their positions onto their trajectories, and these are collected at a detector downstream. So in reality, this is actually what the beamline looks like. Here on the right is the photoinjector, and this is an RF waveguide taking these high energy radio frequency fields into the cavity where the acceleration happens. The laser that feeds or generates the photoelectrons is coming in from the far side of the picture out of view. Here in the center are our different interaction points. As shown, this is our 2 solid state sample environment chambers. And inside these chambers, there's various manipulations for the sample, so it can be kind of positioned and tilted into an optimal configuration. There's cooling fed in to allow a cryo environment. And then from the far side again is the laser pump. At our facility, we're actually lucky enough to have pumps ranging all the way from terahertz in the very far infrared all the way to deep UV, kind of 200 nanometers. Between the sample interaction points and the photocathode is various electron diagnostics and differential pumping, separating the ultra-high vacuum at the photocathode from the more moderate vacuums that we use for the interaction areas. Downstream are the detectors. So here on the right are where our detectors are positioned. You can see this is quite a narrow beamline pipe feeding the diffraction or the diffracted electrons to the detectors. It's worth noting that the cone of the diffraction angle is very small, only fractions of a degree because of the high energies that we're using. So just to take a step back and talk about this diffraction process and how that's occurring. As electrons pass through matter, of course, they interact via the Coulomb interaction. And this is happening both with the nuclear core and the large charges there, but also with the electron cloud surrounding it. And so in UED, from this electron diffraction, we actually get information about both the position of the nuclear core and both kind of the valence and outerlying electrons. And this is well represented by the Mott beta formula. And so here the dependence on the kind of nuclear charge and the electronic scattering are separated out. It should be noted that in general, the nuclear charge dominates and is much larger than this electron cross-section term. So what does this look like in reality? So for, say, a crystalline sample, it's kind of very simple lattice, what we end up is this very typical kind of Bragg-like diffraction pattern. So we get these intense areas of electrons around the center beam. So here is our kind of phosphor screen detector. We have a hole in the center to allow the kind of straight through undeviated electrons to pass. And then on the screen, we collect the other deviations or the other trajectories of electrons. And as you can see, for a single crystal, these are forming into a lattice of peaks. And each of these peaks corresponds to a correlation length within the crystal. And in fact, what we're seeing here is essentially a reciprocal relationship. The real space lengths inside the crystal are being translated into a momentum space separations of these peaks. Now, I just want to show you a very typical UED experiment to kind of give you an idea of what we do before going a little bit deeper. And this prototypical experiment is just looking at the thermodynamics in polycrystalline gold heterostructures. So various films of polycrystalline, thin films of polycrystalline gold were made and encapsulated with either a capping layer of silicon dioxide or with no capping here. And so these were placed into our beam and pumped with a femtosecond optical laser pulse. So this optical laser pulse is coming into the gold and being absorbed via the conduction electrons. So this energy is going into those conduction electrons. And what we're interested in this experiment is how that energy transfers into the lattice vibrations, into those lattice degrees of freedom. And this we probe by using a femtosecond MeV electron pulse in the transmission geometry that is timed to this laser pulse. And so this is our very typical pump probe experiment. As we record these diffraction patterns for different delays, what we see as a function of time, this is the graphic on the right here, is that the various reflections decay. So I would just like to note that here, because this is a polycrystalline sample, instead of getting these very intense peaks, they've now become rings. And this is just simply because all of the different orientations of the crystallites within this sample. But these, again, correspond to these well-defined reflections in the crystal. As you can see, as we go from low momentum space transfer reflections, so this is the 111 peak, which is near the center here, going out to these outer peaks, the pattern, the relative change in intensity gets more and more significant. And this is following the kind of well-known Debye-Waller dependence on these intensities. And from this, we can actually extract the mean square displacements of the atoms as a function of time. And this can be related to an equilibrium temperature. And so by combining all of this, we can actually get this time versus temperature map for the various samples. Here you can see how the sample with a silicon dioxide cap or silicon oxide cap actually has a faster transfer of energy from the electronic system to the lattice than one without. And so here we're kind of able to measure the dynamics of these processes. So after giving you that kind of very basic type of experiment that we do as an example, I wanted to give you a little bit more information about why you might use MEV electrons instead of one of the many other time resolve techniques that can be applied to these science questions. And there are, I think, 4 general reasons that you might consider using electrons. First of all, this is actually quite a simple technique. And one of the reasons for this is because of this high energy. Because we're dealing with MEV electrons, we have a very small wavelength. The wavelength is very much smaller than the kind of separation of the atoms. And this means that we actually have a very flat E-wall sphere. It means that we're getting a very flat slice of momentum space. And so here, for example, for a nickel oxide diffraction pattern, we can see peaks going all the way out to at least 1200. And we're getting a lot of information from all of these different peaks in one single measurement. And because this is a very flat sheet of momentum space or a flat cut of momentum space, this is quite easily interpreted. It's very easy to see what's going on and what orientation we have here. And this is very helpful as we get to more complicated structures. Secondly is the sensitivity. And in some ways, this is a little bit of a double-edged sword. Electrons have a very high cross-section. It doesn't actually take up that much material to get into a multiple scattering regime or to really attenuate that through beam. Typically, for our transmission solid experiments, we're dealing with samples that are between 0 and 500 nanometers. That kind of stopping range can be as low as 100 nanometers, but depending on Z, it can kind of move up to maybe about a half micron. But in general, we're dealing with thin film samples. On the beneficial side, this does mean that we can make measurements or get a lot of scattering even from things like single atomic layers. And that enables studies of these kind of thin film type heterostructures. Secondly, because of this sensitivity, both the nuclear core charge and the electronic cloud, we can see things like, say, the proton in chemistry, which is more difficult with things like X-ray techniques that are only as sensitive to the outer electrons, or to the photoelectron cross-section. Third, because we're dealing with relativistic electrons, it means that the Coulomb effects of space charge blowing up the electron bunch and smearing our time resolution are reduced. So we can maintain a short pulse over a longer propagation distance. And this allows more development of the sample environment around this. At the moment, the instrument has an overall time resolution of about 150 femtoseconds. The actual electron pulses are about 70 to 80 femtoseconds long. This relativistic nature of the electrons also, when compared to, say, KV electrons that are more typically used in electron microscopy, it does mean we have a slightly better penetration depth, or we can stay in a kinematic scattering regime for a lot thicker of samples. And so most of the kind of sub 100 nanometer samples that we're measuring, we're staying more or less in this kinematic scattering regime. Finally, I think probably one of the least appreciated parts or things about MEV electrons is that they're a relatively gentle structural probe. there's actually not as much energy deposited per scattering event as per X-rays. And this graph kind of illustrates this and showing as a function of atomic number for all the elements, a comparison of the number of scattered particles you can get per quantity or per unit of energy deposited into the system. And you see in this kind of relative comparison between various energies of X-ray going from about the kind of 9 keV that's typically used at LCLS 1, going up to the kind of energies accessible at now accessible at LCLS and other expels, that over the full range, we have still between a few tens of times to about 1,000 times advantage in the number of like quanta of scattering information that we can get for like a unit of deposited energy. And so this matters when going down to very thin and very small samples, where the probe can actually start can start to pump the structure, and where you may not want that much energy deposited into the system. Okay, with that, I want to take you through a couple of illustrative science examples, just to give you kind of a flavor and overview of what the instrument is capable of doing. So first of all, kind of going over to the chemistry side, or photochemistry side. This is a great example of the type of measurement that we've been doing on cyclohexadiene. And so using a gas cell inside the chamber, we're able to explore chemical reactions initiated by a laser pulse. In this case, the CHD molecule, upon UV excitation, the carbon-carbon bond is broken. And so then the structure evolves and the molecule stretches out over time. MeV-UED allows us to follow this in real time through this process. And this then can be used as a benchmark against quantum simulations of this process. And you can see here, lower panel, that the data and simulations match up really well. Another excellent example coming from the solid state area is exploring thermodynamics across heterostructures. In particular, this work was looking at this across a van der Waals bond. And so looking at this heat transport between two monolayer films with this van der Waals bond in between, and understanding the physics of that process. And so via the electron diffraction pattern, which is shown here, we're able to see able to identify the actual peaks of the individual monolayers in this heterostructure. And then via different ways of applying energy and heat through this heterostructure, we're able to measure basically the thermal resistance between these two layers in a kind of a device-like structure. And so via this Debye-Waller effect, you can see the temperature difference and how that evolves. Finally, we're also actually able to make momentum resolved measurements of phonons. And so in between these reflections, so in between the kind of Bragg reflections that we get from a typical diffraction pattern. So this is a diffraction pattern on nickel. And here we've kind of zoomed in and just changed the color scale to remove these reflections. What you see is intensity appearing in between the peaks. And this is the thermal diffuse scatter. This is the scattering of electrons from phonons. And by measuring this in a time-resolved measurement, we can actually see how those phonon populations are evolving. And so as a function of momentum across the brilliant zones, we can see those phonon populations and how that system thermalizes. And so this was a study looking at this dynamics of the phonon populations after excitation in single crystal nickel. So finally, I just wanted to give you a flavor of the outlook on this instrument, and we're very committed to the continual development of our instrument here at SLAC. We're preparing currently for a second liquid phase run with a liquid sample environment, which will occur middle of 2024. Here, a thin film liquid jet can be probed using the MeV and can start to look at those liquid structure dynamics, both statically and with an optical pump. We're also very committed to the development of our instrument and the source. And so here on the right, we kind of show the kind of next stages that we're planning on the development of our instrument. So in red, or these red squares, kind of outline our current instrument capabilities in terms of the number of electrons we can actually use at the sample position compared to the kind of instrument time resolution. And we're hoping within maybe the next year or so to have extended this out to kind of have reduced this closer to 100 femtoseconds time resolution and significantly increase the flux by going to a higher repetition rate of electron source. And then in the next following years, we're hoping to further reduce the time resolution to get to much faster dynamics and continue to improve the source brightness as well via developments of our gun. So after giving this kind of overview of the instrument and what it is capable of, what I really wanted to then share was some information about how you can access this MeV-UED user facility, or as part of the LCLS user facility, and how you can get time for your own science. So access is via proposal calls. And these typically happen about yearly for the MeV-UED instrument. We are focusing usually on one sample environment for a proposal call. For example, for either gas phase samples or solid state samples, or in the future, probably also for liquid phase samples. Proposals, which are typically 4 to 6 page submissions of the science you'd like to complete, are submitted to an external committee, which vet the scientific merits of the study and give the facility feedback on which would be the most beneficial to proceed and happen or be allocated beam time. Typically, the beam time assigned is between 4 and 5 days, which is our typical experimental length. And we run and collect data over 24 hours for those 4 to 5 days. If you are interested in developing a proposal or just want to see the possibilities, please reach out to me and to our other instrument scientists. And we are very open to kind of helping you develop the best possible proposal and giving any additional information that you might need to make that proposal. Just for information, we're expecting that the next proposal call will be focused on the solid state sample environment. This proposal call will most likely come out at the very beginning of 2024 for experiments that will happen towards the autumn, towards the end of 2024. Please see our instrument page on the LCLS website for further details and just for more general information about the instrument and the contact details of all of the scientific staff that are involved. And also, if you are not already, I would encourage you to subscribe to the LCLS Users Office. You can find information about that on the following link. And that includes a subscription to the mailing list where you'll hear about proposal calls, both from the MeV-UED facility and from all of the other LCLS instruments. So with that, I would just like to thank and acknowledge both first and foremost, the Department of Energy, which funds our facility and allows all of this excellent science to occur. And then also my sincere thanks to the whole MeV-UED team presented below. And thank you very much for your attention.